Hello everyone. For this tutorial video, I'd like to explain limits at infinity of more sophisticated functions than simple polynomials and their ratios. For example, if we are told to evaluate the limit as x approaches infinity of e to the power of x, and also evaluate as x approaches negative infinity, and then repeat the process for e to the power of negative x, we would see by consulting the graph of e to the power of x that as it approaches infinity, the function approaches infinity, and similarly, as it approaches negative infinity, the function approaches 0. With some creative thinking, we can see that e to the power of negative x is simply e to the power of x flipped relative to the y-axis. So it follows the limits should be backwards, i.e. the limit should be 0 at infinity and infinity at negative infinity. Since we have figured out the basic types of limits at infinity of e to the power of x, we can evaluate e to the power of more complex arguments, such as this one. Our shortcut we can do to evaluate the limit of the argument is to note the highest power, similar to what we did in the last video, as that will have the greatest amount of increase and therefore the greatest influence on the function. So because we have negative x squared as our power furthest away from 0, we can guess it has the greatest influence on the function. So the limit of it would be negative infinity. And so we do e to the power of negative infinity and figure out the limit of that as x approaches infinity. We remember that e to the power of negative something means that the function decreases. So it follows that e to the power of negative infinity means the function is so small that the limit approaches 0. So our final answer is that the limit is 0. More sophisticated cases, as z approaches 0 from the right, we want the limit of e to the power of 1 over z. Although we might not have been asked a limit at infinity directly by the problem, it will evaluate to a limit at infinity, as we will see shortly. We know that the limit as z approaches 0 from the right of 1 over z equals infinity. So now we have the limit of e to the power of infinity. And as the exponential is positive and increasing, the function is positive and increasing, so the limit is infinity. Now that we've figured out cases with exponential functions, we can figure out cases with logarithms. We know from a previous video that as the logarithm approaches 0 from the right, the value of the logarithm approaches negative infinity. And we will see now that as x approaches infinity, the logarithm will approach infinity too, which we can consult the graph if we are not sure about this. These two basic facts are a setup to evaluating the logarithm of more complex arguments, such as this logarithm, as t approaches negative infinity. Because we have a constant over a polynomial, whose fastest changing term is positive, this means the limit would be 1 over positive infinity equals 0. So we substitute in 0 for the argument of ln. We remember that as x approaches 0 on the ln graph, the function approaches negative infinity. So as a result, the overall function has the limit negative infinity. The final type of more sophisticated graph we'd like to look at is inverse tangent, which gives us pi half if x equals infinity and negative pi half if x equals negative infinity. So if we are asked the limit as x approaches 0 from the left of inverse tangent of 1 over x, we would see that as 1 over x approaches 0 from the left, the function approaches negative infinity. And we see graphically, as the argument of the inverse tangent approaches negative infinity, the inverse tangent itself approaches negative pi half. So our final evaluation for the limit is negative pi half. Now that we have figured out more sophisticated types of limits at infinity, we can discontinue computing limits for a little bit and go back to discussing concepts related to limits. In particular, we are ready to discuss more formally what continuity is for a function. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.